inside of there.
Through. And I forgot the IH bar, and that was the problem.
Yeah, so little details, all right? The only thing in there is that I started worrying that someone might be able to try to normalize this thing. And did I normalize this in class?
No.
I absolutely did.
Well, you said it's n times.
In class, I went through and I normalized this thing, and we figured out that fact exactly. Griffiths just says this is the normalization.
We found the spherical harmonics for 0, 0.
That's right. And then we had to integrate the whole thing, psi star psi, over the whole volume. And the volume is spherical, so it's r squared sine theta, d theta, d phi, right?
I thought you wanted us to do that.
So here's what happened is that if you did that, I was happy, and you started to do it, Alkmaar, I think. Didn't quite get it.
No,
Right. But here's, if you just left it like that, I would have been okay, because I didn't give you the y0 spherical harmonic, which is the 1 over 4 pi, which cancels when you integrate over the solid
Right.
angle.
Okay, I knew that though. So the
Yeah.
y00.
Yeah, it's
Just
just
1
the
over 4 pi.
Yeah. All right, so it's just a fun problem, and it's a great problem, okay? All right, then the next thing was on the commutation relations, and it was just, you know, do you understand how to do a commutator between the position and momentum? And the commutation does not come out to be 0, all right, which means there's at least one state where you can't get simultaneous measures of the momentum and the position, okay? But if things do commute, then indeed there are eigenfunctions that contain simultaneous eigenvalues of both those operators. All right?
That's the definition of
That's the whole purpose, yeah. So when they commute, they share the same eigenfunction, and that eigenfunction has simultaneous eigenvalues of the two operators. All right, and then problem number 4 was homework problem number 37. All right. So I did it by hand, and it's, you know, not hard to do it all by hand. But the other thing that I did is I asked you guys to start playing around with the maxima. All right, and what I did is I did that example problem of the electron and the electron neutrino oscillations using maxima. And it just, all you do is you input the Hamiltonian. Then once the Hamiltonian's in there,
That's about right.
oh, okay, thanks. And then once you input the Hamiltonian, you just say eigenvalues, it gives you the eigenvalues. You say eigenvectors, it gives you the eigenvectors. Right? And so I said when I did the three-dimensional one, oh, how nice it is to do a three-dimensional one, not to have to work hard. And so the whole work in that problem was really finding the eigenvalues and eigenvectors. And so if you guys had gone home and practiced the maxima, I know we had the issues with the computer in the class, but it was, you say Hamiltonian, you write in A0B, 0C, 0, A0B, whatever, okay. And then the next line you go eigenvalues, it goes A minus B, A plus B, C. And then eigenvectors, and then it gives you the eigenvectors, what was it, 1, 0, 1, 1, 0, minus 1, and then 0, 1, 0. Yeah. And then the rest is just, you know, doing that expansion.
I just haven't taken linear algebra.
What's that?
I haven't taken linear algebra yet, so it's like I forgot like how to do like how to multiply the matrices. I just got stuck.
Okay, yeah, multiplying the matrices. But that's why I said use maxima. So we did the two-dimensional case. And if you did the two-dimensional case, and that's what I suggested doing, and I put on the blackboard, the case with that two-dimensional case of using maxima, and you see how easily it comes
Yeah, you
out.
had like your 4-color plot online there.
What's that?
You had your 4-color plot. Orange, like 4 different colors for the plot.
Okay, yeah, whatever.
That was nice.
Okay, so you know, go do those things. Oh, and then once you get the basis set, and then the answer is that then once you get the basis set, once you have I mean we're solving this problem. H psi ket equals, you know, E psi. So what we did, these are the eigenkets. We found E1 equals A minus B, E2 equals A plus B, and then E3 equals C. And so then if you do this by hand, what you've got to do is you've got to put these back into the original equation and solve for those particular eigenfunctions. So these are the three eigenvalues, all right? But instead, what I did is I used, maxima. So the eigenfunction that came out for this, or the eigencat, was 1, 0, minus 1, right? But remember, it's got to be this. So now this is, so remember, when we solve Schrodinger's equation, we get the stationary state solutions, right? And those stationary state solutions have to be normalized. So this becomes 1 over radical 2, 1, 0, minus 1, right? To normalize it. Okay, but now I'm normalizing in my head. This one came up to be 1, 0, 1. So this came up to be 1 over radical 2, 1, 0, 1. And what does this one come up to be? It came up to be 0, 1, 0. That's it. So this is like psi 1 ket. This is psi 2 ket. And then this is psi 3 ket. So what collectively, what is psi 1, psi 2, and psi 3? Those are that's our complete basis set. Right?
And because, because the Hamiltonian's Hermitian, is it an orthogonal basis set?
Yeah, all that stuff.
It's
orthogonal,
it's
it's complete, it has all the properties, this stuff of dot products, and so it's Hilbert.
Right.
Right? It's just finely dimensioned. All right? And then once you get a complete basis set, right? Then don't you just do this? Don't you just go psi general of T equals what?
C sub n.
Summation over n of C sub n e to the minus I e sub n over h bar t times psi
sub n.
All right. And now, how many n's do we have? We have 3. So we have E1 is A minus B, n equals 2 is A plus B, E3 is C, and this thing. How do we find the CNs?
So C sub n is equal bra psi sub n ket psi sub n. Yeah, big psi sub n is 0.
All right.
But big psi sub n of t equals 0 is just essentially little psi sub n, isn't it?
This would, well, let's do, so one of them was, yeah, so one of them was, so for the first one, A was psi sub t equals 0 equals
0, 1, 0.
0, 1, 0, was that it?
Yeah.
Okay, so let's do it.
Well, we already know that 0, 1, 0 is psi 3.
Well, let me just do it out. So, I'm going to have 3, so I call these C A minus B. That's going to equal, you ready? 1 over radical 2, 1, 0, minus 1 times 0, 1, 0. What does that equal?
0.
0. Then C A plus B equals 1 over radical 2, 1, 0, 1, 0, 1, 0. What does that equal?
0.
0. And then C equals 1, 0, 1, 0 times 0, 1, 0. What does that equal?
1.
1. So the answer is that psi of t equals e to the minus c times t over h bar, right? Times, if you want, what did I call it over here? Psi 3 or psi c. That's it. And that's the full time dependent one. All right. The other one was more interesting. You had to add. I think B was more interesting. You had to add together a couple. And you had
Right, it's a linear combination of
It's a
stationary
linear
states.
combination. So now you have exponentials of E minus B, and then an exponential of E plus A plus B, and then A minus B. So then you get funky time dependence. All right. But look, guys, is this anything different than we did right from the very beginning?
No.
And it really isn't. All right? And that's the whole theme that we've done through here. It's been over and over and over again. We solve Schrodinger's equation to get a nice stationary state infinite basis. And then once once you get a nice basis set, what do? You expand onto it. All we're really doing, if you think about it, is Fourier analysis, right? Isn't Fourier analysis just find a nice basis set, and then you expand everything in terms of that basis set, and then you find the coefficients? All right, and so what we're doing in quantum mechanics is we're using Schrodinger's equation to find the appropriate basis set to use. And then once we find the appropriate basis set, we're looking at just the expansions of it. Right? So it's what we're doing over and over again. We did it with functions. We did it with three-dimensional functions. We did it with infinitely basis sets. And instead of being a summation, you become an integral and you talk about wave packets. And then we made it all complex and we did it in terms of vectors and matrices. Okay? So that was a test. I thought it was a good, fair test for the stuff we've done. All right, so next up we have the final. All right, and the final will be, I believe it's going to be Thursday, a week from today. Okay, at 8 o'clock in the morning. It'll be 2 hours, and it'll be closed book and closed notes. And my advice is do the things that I've done in class mostly. You know, and then if you want to concentrate on homeworks, concentrate on the homeworks that I've emphasized. You know, especially in this book, there's a lot of the homeworks that I haven't emphasized that have to do with some proofs and things. I'm not going to go there. All right? So the problems I've emphasized are essentially the problems that I think are reasonable and that can be done.
Also spin.
And then we're going to finish up a little bit on the spin today, okay? All right? All right, guys. Let me pass this back. And so let's finish up spin.